Welcome to BC Calculus video for skill number 225. I can employ implicit differentiation to find derivatives of implicitly defined functions. And the saddle trivia question for this video is, featured below is a bicycle with a bicycle saddle, and there's a special name given to this type of bicycle saddle. What is that name? Alright, so if we're going to talk about implicit differentiation, we should talk about what makes an implicit function or an implicit equation. So most of our math career we've been looking at explicit equations, equations which are either in the form y equals a function in terms of x, or maybe they're rearranged but we could very quickly solve it for y. So this one we could solve for y by subtracting 2x. This one we could move the x squared minus 9 over to the right hand side. This one already is solved for y. So all four of these equations can be written in the form of y equals f of x. An implicit equation is an equation that cannot be written in that way. So we could try to solve this equation for y, but chances are we would be running in circles or hitting a dead end, whichever path we took. So this is considered an implicit equation. The most common implicit equation that we've seen to date is the equation for a circle. So if we solve that for y, we would get y equals the square root of 1 minus x squared, but in truth we actually have the plus and minus, the top half of the circle and the bottom half of the circle. So that's two separate equations. Implicit equations can get very, very complicated. They can involve more than just two variables, but we're going to focus on variables or implicit equations that use just two, maybe three variables. When we're trying to find the derivative of it, we actually wind up using the chain rule, and that's why we learned skill 224 first on the chain rule. So let's take a look at this. Let's solve one of these, find the derivative of one of these equations. Example 1 asks us to find dy dx, so the derivative of y with respect to x, for the equation x squared plus y squared equals 36. So for those who remember what that looks like, that's actually a circle with a radius of 6. So if we want to do that, what we're going to do is we're going to take the derivative of each term with respect to x. So the derivative of x squared, the derivative of y squared, and the derivative of 36, all with respect to x. So we use our power rule. The derivative of x squared is 2x. We can use the power rule again. The derivative of y squared is 2y, but since we are taking it with respect to x, we have to multiply it by the derivative of y with respect to x. We could, if we wanted to, write this as 2x plus 2y y prime equals 0. That's prime notation. And then, since we're looking to solve for dy dx, we want to isolate dy dx. So I moved my x values over to the right hand side, and then if I'm trying to isolate the dy dx, I'm going to divide both sides by 2y, and that gives me dy dx is negative 2x over 2y, and the 2's cancel. So that gives me my final answer of dy dx equals negative x over y. We could use this if we wanted to, say, find the tangent line at the value of x is 5 or something. We won't look at examples like that in the video, but the process holds the same. Now that we have an equation to find the slope, we can plug in the 2 points and plug that into the point-slope equation to find the equation of our line. And we'll see some of that in the homework exercises. Alright, moving further down the page, I kind of gave a summary of what exactly we did. First we differentiated with respect to x, and that was our first step up here. Then we used the chain rule whenever we differentiated y with respect to x. So this piece here we are differentiating y with respect to x. And then everything below that was rearranging to solve for dy dx. Example 2 is good because we're not restricted to the variables x and y. In this equation I'm using the variables s and t, and I do that to kind of break you of the habit of always thinking that it should be y prime, and really looking at what is going on when I'm saying find ds dt. So what I'm saying is we should be differentiating with respect to t. So I start out the equation by writing d over dt of the whole equation, and then I can break it into its individual terms. The derivative of t to the third, the derivative of s to the third, and the derivative of 6ts. So if we take the derivative of t to the third with respect to t, we just get the power rule, 3t squared. If we take the derivative of s to the third, we get 3s squared, but we were doing it with respect to t, so we need to apply the chain rule and add on the multiply of ds over dt. And then in the final step, or final derivative, we're looking at the derivative of, you could argue that this is the product rule. We have 6t times s. So we have our initial times the derivative of our second plus the derivative of the first times our second. So that's the product rule being carried out there. Now the question asks us to solve for ds dt. So now that we've taken the derivative, we're just rearranging to solve for ds dt. So we're going to take all of our terms that have ds dt and put them on one side of the equation. And then we're going to take our terms that lack the ds dt and put it on the other side of our equation. What that allows us to do is it allows us to factor the ds dt out of the left-hand side of the equation and arrive at something that we can divide. So in the final step we're able to divide out the 3s squared minus 6t from both sides. So we divide 3s squared minus 6t from both sides, and we get our final answer of ds dt. It is important to note that sometimes after you get there you might be able to factor something out, and in this case I was able to factor a 3 out of the top and bottom. So that allows me to get a cleaner final answer in the end. There you go. That's taking the derivative of something that's not with respect to x, but actually to a different variable. Got one more example here for you. Alright, in this final example I'm going to use prime notation, so you can just see it worked out with prime notation. Also it's a good example because we have to employ a little bit of the chain rule as well as the product rule. So I'm asking you to find the derivative of y with respect to x for this implicit function. And what we can do is we can say take the derivative of the whole thing. So if we take the derivative of the left side, we're going to use the chain rule. Derivative of cosine is negative sine of the inside times the derivative of the inside. So I write y prime instead of dy dx. And then on the right hand side we're going to use the product rule, and what we have is basically x times y squared. So the product is the derivative of x, which is 1, times y squared, plus x times the derivative of y squared, which is 2y y prime. When we go about solving this for y prime, what I want to do is I want to take all pieces that have a y prime and move them to the left side of the equation, and all other pieces can stay on the right side of the equation. I then factor out a y prime, getting this equation here, and with that y prime factored out, I can divide both sides by the remaining factor, giving me the final answer of y squared all over negative sine y minus 2xy. Thanks for watching the video for Scale 225, and the saddle featured in this bicycle is called a banana seat. Thanks for watching.